Hi everyone, welcome back. We complete with the microcorruption series. Today's challenge is really interesting one. Like, to be honest, this one was one of the few challenges that I really had fun solving them. So the challenge name is Halifax, um, and I would recommend anyone who is watching the video now to try the challenge on his own before trying to solve it, or before watching me trying to show you how to solve it. Well, this challenge, to be honest, took me 2 weeks to solve, but I really had fun solving it. Especially the stuff that I did along the way really was wonderful, to be honest. I was really having fun solving that challenge. As I thought, in order to complete the microcorruption, we have to upload all the videos about the microcorruptions. And in order to for everyone to learn something out of these videos, like you should just try to solve the challenge on your own before watching me. This is the key point that I wanted to explain. So let's not waste too much time. Let's try to solve together. Yeah. So overview. So this new lock adds a hardened mode and disables the 0x7f interrupt. So if you remember, the 0x7f interrupt is the one that we have used until now to open the door. Whenever we have the chance to execute some code, we usually execute the code that can open up the door using this interrupt. So we usually push 0x7f and then we call the interrupt. And in order to do that, we just use 2 lines of assembly to just open up the door. Now, I think this new locks adds a hardened mode and is actually disabling this interrupt. Okay, interesting. So let's read the details. An example in field debug payload follows. So any payload is allowed because the unlock key must be passed to the new interrupt with code 0x41, and this key is only stored in secure memory. So I think now he's gonna be disabling the 0x7f interrupt, and in order now to open up the door, we need maybe to give the key and call the new interrupt, which is 0x41. But here's one thing to say about this 0x41 is that they had a mistake with this 0x41. It's not the interrupt that is going to be used to open up the door. It's going to be 0x42. After just some several tries alone, I just figured out that in order to open up the door, we need to use the interrupt 0x42. We'll just came back to that at the end of the video in order, just after retrieving the password. So the idea of this challenge is to find out a password that can open up the door and give it with the interrupt 0x42, and that's it. That's all what you need to open up the door, I think. So let's just try to run run the binary. So what do we have? Welcome to the test program loader, enabling hardened mode. So we are verifying that the 0x7f interrupt is disabled, and then the 0x7f interrupt disabled key stored in the internal SRAM, and we unlock by providing the 16-byte key to the 0x41 interrupt. Okay, so the key size is 16. Okay, this is interesting. Internal SRAM hash. So this is a hash of the RAM, and then we just enter some payload, just some debugging payload. Okay, I think it's time to just read all of that, just statically to understand what this program is doing. Then we will try to craft a payload and see what's going on inside of this code. Yeah. So I have tried to do that before just making the video. Try to comment some of the parts of the code just for you so that you can understand directly what I'm talking about. So we take a look at the main. Just let me get the music a little back. Yeah, cool. So So the usual stuff. So just some stock alignment. So we'll come to the test program loader. Then pushing some stuff, then doing some interrupts. Then he's verifying that the 0x7f interrupt is disabled just by trying to call it, and then checking the result. And then if the result is cool, then the 0x7 interrupt disabled is disabled, and the key stored in the internal SRAM. So one thing to say in this challenge, guys, is that if we take a look, we see that the key is stored in a secured memory, which means that the key is in the SRAM. So he is basically in the memory, but we cannot access the memory and get the key directly. So this is the point that you have to understand. So because if we know the key, we can just directly execute a code that can just call the interrupt 0x42 with the key that we want to try. We can just do that. We can try to craft a code that can do that and directly pass the key. But the key is supposed to be secured, or is supposed to be is supposed to be in the memory, but the memory is not accessible directly. This is the point. So unlock by providing a 16-byte key to the 0x41 interrupt, and then another put. Then he's moving some values, and then there is a memory set, which means that he's going to be initializing some of the memory. Then he is moving the string internal SRAM hash, then again calling the puts. Then, now this is the interesting point, well, the interested part. So he's moving the stack pointer to the register 13, then he's moving this address to the register 14, and then he's clearing the register 15, and then he's calling a function called SHA-256 internal. So this SHA-256 internal is a function that is used to hash bytes of data. So for example, you give it a data, and it's gonna be giving you the hash. So for those who don't understand what a hash is, you can just imagine. Just to explain to you what hashing is for the people who don't know what hashing is. So hashing is basically, for example, when we do, if you remember the symmetric and asymmetric encryption, if you have watched the video of the IS EBC, hashing is not like encryption. It's not the same as the encryption. For example, when we encrypt something, we actually um, we actually generate a cipher. Let's say it's gonna be just generating a cipher. To decrypt that cipher, we actually, this is the encrypt and this is the decrypt. So you basically give the cipher, and then you get the plain text. So this is gonna be just plain text. So this is a plain text. And when you have the cipher, if you pass it to the decryption, you get the plain text. So basically, you have an encryption function and you have a decryption function. Now, when we are talking about hashing, hashing is not the same as encryption. For example, when you have a plain text and you hash it and you pass it into a function that hash, you actually create a hash. For example, in our case, the function that is going to be hashing the plain text is going to be called SHA, or SHA 256. 256, that means that it's going to be giving us a result on the 256 bits, which means it's 32 bytes. So it's going to be giving you the hash. Now, taking that hash, you are not supposed to know what the plain text is, because when you hash something, you can't go backward. So hashing functions are irreversible. Yes, this is basically what hashing is, and we usually use it, for example, to verify the integrity of something. For example, if you remember the signature part, for example, let's suppose I have sent a data, and to make sure that my data was not um, my data was not modified by someone else in the road, I will be sending the data and sending the hash of that data. So that, for example, when someone wants to know, for example, if my data was right or not, he could, for example, hash the data that he have and try to decrypt the signature. Well, basically, this is the signature, but the signature is we usually hash it. Anyway, just you don't have to take too much attention on that. Now let's just go back to the challenge so they can understand what I'm talking about. Yes. So we have now the internal SRAM hash. So what he's gonna be doing, he's gonna be hashing the static RAM, which means that he's gonna be hashing all the RAM, all the bytes in the RAM, and giving us a hash. So how he's going to be doing that? So the parameters of the SHA-256 internal are going to be the hash destination, where are we going to be storing that hash, and then the amount of data or the amount of bytes that we want to hash. So this is the amount of data that we want to hash, and then the offset where we are going to be starting the hashing. So we are going to be starting from 0. So we are actually hashing the data from 0 to 0x1000, which means that he's going to be actually, if we just go back to the challenge, he's going to be hashing the data from this place to the end, to just the address 0x1000. So he's going to be hashing that part of the data, of the RAM, I'm sorry. So and then he's gonna be printing that hash just using this block. This is just a simple block that's gonna be using some boots and some bootchar actually to print the character of the hash. Then he's gonna be printing for us, please enter debug payload. So just to give us the payload that we will be given to in order to execute it. So he's gonna be moving 0x400 to the register 13, then he's gonna be clearing the register 14, and then calling the memory set. So the memory set is just initializing the buffer where we will be loading the payload that we will be giving to the program. Then what do we have? So this is the get string. So he's gonna be just reading the input that we will be given. Then he's moving the address. Just one thing to mention here is that the destination that we will be that our data will be loaded at is the 2400, which is the usual just address that he uses almost on all the microcorruption challenges that we have played. So he's moving the first byte to the register 11, and then he's swapping the bytes at the register 11. Then he's moving another byte into the register 15, but it's actually the byte that is after the byte that we have loaded. Then he's gonna be doing OR, just an OR operation. This is basically for the OR operation. Well, this is the address where the code will be copied. And then we have the byte, which is the size of the code. I actually just came to the conclusion that this is the size of the code because he's gonna be comparing it with a 2. If it's not valid, which means that if it is inferior to the 2, then obviously it's an invalid payload length. Otherwise, he will be just printing for us, executing debug payload, and then he's gonna be copying that code into the memory. So he will be taking um, this is the size of the code. He will be loading that into a register 13. Then he's gonna be moving what's after the 2402, which is the 2103, into the register 14, and then this is actually the offset of the code that we will be executing. And then he's moving again the destination offset, which is in the register 11, as we have just mentioned. He will be putting that into the register 15, and then calling the memory copy, which means that he will be copying that code into memory, into the destination that we will be giving him. And then he will be calling the R11, which means that he will be calling the offset of the code when it's loaded, just to execute the code. This is what basically, this is just a simple program loader, just a loader that is gonna be loading some program. Now the interesting part, let's try for example to just test the functionality of this program loader. For example, I will be loading my program into the address 5000, and the interesting part is that we don't have to worry a lot about the little Indian in this challenge, because he already did that for us. For example, he already did that. Actually, those instructions are the instructions that are used to make sure that whenever we, for example, we give an address, the address didn't get reversed when it's loaded, or when the program is doing the flow without any kind of issues. Yeah. So basically, for example, now if we give 5000, so this is the address where I will be loading. So basically, I want to load my code at the address 5000. I suppose, let's say I will be loading to a code of size 2. Let's suppose this code is just gonna be a simple return. What is the code? So return. So this is the return. So I suppose I will be just executing a return. So if we try to execute that, we see, for example, if we just go back and try to go to the address 5000, so this is the 5000. So this is my code. So this is the return that we have tried. So to understand more how this program loader is working, we can just, for example, just set a breakpoint there and see how the call is going on. So if we see again, and we say, for example, that I want to load my code at the address 5000 with a size 2, and this is my instruction. He should be now hitting the breakpoint. He hit the breakpoint, and then if I step, as you can see, the instruction now he will be executing is my return. So once he do that, he just returns and then he jumps back. So this is basically how the program loader is working. Now, since we have at least an idea on how the program is working, how can we retrieve the password from a secure memory without having access directly to the RAM? So basically, now if we try to just to draw an image of what we have, so this is basically the program loader. So what we can do is actually we can give it code, and that code will be executed. It does not check if it is signed by the manufacturer of that program loader. It's not checking. There is no security checks. It's basically just executing the code that we give. So we basically have a lot of freedom to do whatever we want. And just if we go back, guys, just to give you, and let me first do something for you. Since we have read the code statically and understood what the code is doing, let's try to reverse engineer the code back and just write it in C so that you can understand more what I'm talking about, and just to understand where the key points are and where the attack factors are and how can we exploit it. So just to go back to the code, I try to reverse engineer, try to just write some pseudocode that can mimic what this code is doing. I'm not gonna be compiling it to C, obviously, but just an explanation for you so that you can understand more what I'm talking about. So basically, let's suppose we have so the first thing, just to try to mimic what this code is doing. So he's obviously just printing the messages. So puts so he's putting some message there. Welcome to the test program loader. This is the first message. The second message is he's gonna be putting another message. It's just enabling the hardened mode. And then he's actually calling the interrupt. So the interrupt, I will just call it, for example, like that. Interrupt 0x 100, since he's actually just calling that one. So yeah, so this is basically what he's doing. Then he is just verifying that one. So Okay, so verifying verifying 0x7f is disabled. I'm just trying to reverse back the code for you so that you can understand. So, because like we cannot just try to solve the challenge without having an idea where the key points are, where the attack vectors are, where is the vulnerability inside the code. We need to know that in order to solve it. Then once we do that, once we verify that, he actually try to call the interrupt 0x7f. So to do that, he's 0x7f, and then he puts again um I think, yes, this one. There's a lot of messages, to be honest. Then he's unlocking again. Okay, then he's setting the memory, so memset. um well, the memory set is actually working on the stack pointer, so we need to maybe just create a stack pointer, just a variable stack. Let's just suppose, let's just call it stack memory. Let's suppose it's the size. Its size is gonna be 30, for example. Okay, so he's gonna be memory setting that stack memory. He's gonna be setting that stack memory, for example. What is the size that we have? Um, so basically, he's gonna be setting zeros, obviously, with the size of the 0x20. Okay, so he's gonna be initializing the stack memory, just the first 32 bytes with zeros. Okay, now the next thing that he's gonna be doing, so he's putting something, which is internal hash, another message, SRAM hash. And then calling the function SHA-256. Um, Basically it takes three parameters. The first parameter is gonna be where we are gonna be starting the hashing. So we are starting from 0 to 0x1000, exactly from the what is the hash destination. So it's the stack memory because we are passing down the stack. So this is the stack memory. Okay, now once we hash that, we actually have this loop. Let's just call it a function, just print hash. We can just call it print hash. Then we came to the point where we are gonna be doing something for infinite time, which is we will be loading the payload over and over again. So while true, while we are just having some payload, we will be loading some payload. So puts please enter a debug payload. Now once we do that, we have another memory set. So we are initializing some memory. So memory set the address 2400 with 0, and with we are actually just initializing 0x400. What else? So we are getting some string. Again, we are loading the data inside of that address that we have initialized, I suppose. Yes, and the size of the data is 0x3ff. Yeah, cool. So if this size, there is a size, I suppose. Um, there is a size, I think, I suppose, at the end of that. Yeah. I suppose we should be trying to get a size. So int size equals to actually the address, or what the address is pointing to at this one. Yeah. Yeah, 2, sorry. Yeah. And basically, we need to know what this address is having exactly um, in order to know exactly the size. Yeah, I suppose. I suppose we should know that, so we should know the size of the code, which is at this address. So let's try to do if the size. At the end, it's just some pseudocode. It does not have to be executable. So if the size is inferior to the 2, then we can just put um, invalid something, I suppose. Invalid. I forgot. Invalid payload length. Yeah. And we just exit, or maybe just continue. Otherwise, since it's in a while. Yeah, obviously it's in a while. Otherwise we just put executing payload, I suppose. We just memory copy the code into the destination. I suppose what is the destination that we have? So the destination is gonna be the offset at the 0x 200 or 2000. Hmm. Yeah, it should be the 2000, I suppose. So 0x 2000 from the 0x to 1043, since the code is that address, and the size is gonna be the size that we have, which is that we have retrieved from the 0x 2002. Yeah, and actually we should cast that into a sources to tell him that we are just reading just a 1 byte for him to understand that we are reading 1 byte of data. Because if I just say, for example, that I have a size and an integers, I don't know, maybe it's just I'm trying to make it somehow work and see, but I'm not gonna be compiling that at the end. Just trying to mimic the code and see. Does not have to be. Yeah. So yes, and then I suppose we just have to execute the code. But we are executing the code. Yes, at 2400. Yes. This is just a call at the end. Call the code. Yeah. So if you take a look, guys, at this, there is an interesting thing here. Is that the functions? If you take a look at the code, especially the code of the hashing function, we can actually, if you just see, it's not actually this hashing function. It does not check, for example, if we are hashing some data, or if it's gonna be checking if the range of data that we are hashing correct is in the correct range. If, for example, if I try to just hook this function and try to call it on my own, just writing custom code that can hash functions or that can hash data. For example, if I call, here's the idea of the challenge now. Now you just have to focus with me just on the idea on how are we gonna be doing this. So this is a very fun way to do that. It's almost like the same attack as the return-oriented programming, but except that we are not returning to something. We are actually gonna be using some gadgets of the code. So I'm gonna be using some pieces of this code, just try to write my own code that's gonna be using those functions. So basically I'm gonna be using this function since the RAM is secured and the password or the key is in the RAM. I'm gonna be using this hashing function to leak the password out of the RAM. This is my idea basically. So since we can give code and execute it on this program, basically this is the RAM and it is secured, which means that I cannot read directly from the RAM. But the interesting part is that I can use the hashing function to hash some of the bytes of the RAM, which means that, for example, if the RAM is starting from 0x00 to 0x1000, then, for example, it has a lot of bytes. Let's suppose that the first byte of the RAM is A. If I try to call a function SHA-256 from 0x00 with an offset of a 1, for example, and tell it, for example, to give me the hash of this A, I can get, for example, I can hash that. For example, I can hash it. I can, for example, get a hash. For example, A, B, 2, 3, like whatever. Once I leak that hash out of the memory and I can see it, for example, in front of me, I can just try to write a code that will be just cracking that hash just to retrieve back the A. And using that way, I can basically leak all of the RAM just by using this function. Just by using this little function, we will be trying to leak the hashes of all the bytes in the SRAM or the secured memory, and then I will be trying to crack each hash alone just to retrieve back the original RAM. And then I will try to find the key inside of the RAM. And once we find the key, once we find the offset of the key, we basically try to solve the whole solution. How do we say this? I'm gonna be trying to solve the whole problem. I don't know if you understand exactly what I'm telling you guys, but once we try to leak the RAM just using this hash function, then we can crack back the hashing. Or the hashes, I'm sorry. Once we crack the hashes, then we can get the bytes or the original bytes that we have. And cracking those hashes is easy, guys. Do you know why? Well, it's simply because I'm gonna be hashing each character alone or each byte alone. So, for example, if I wanna just hash an A, for example, hash it. There is no salt actually. Salt is something we add to make the hashing more secure, and you basically get a hash. Basically, since the length of the input is just 1, I can just go from 0 to 50, 250, 55 and try all the combinations and to brute force the hash and find the original byte of that hash. We can just do that simply to crack the hashes, which is the right way. So now the first thing that we have to write, guys, now, I think, is we need to find a way on how we can leak the RAM and make sure that we have leaked the right bytes, and then um, we have to try the different keys that are in the RAM. Now, the first step that we have to do, guys, now is to try to leak the static memory or the SRAM just using this hashing function. So to do that, we have to write now some assembly code that's going to be executing on the program of the card that will be executing. And once we have that, maybe we can just go back and think more about what we can do. So the first step now that we have to do is we have to leak the RAM. This is the first step. So for example, let's try now. Let's just think a little. How can we leak the RAM? So for example, here's an idea. We can just, for example, hash each byte of the RAM and just send it to a place in the memory. For example, we have a lot of addresses on the memory. We can use them. For example, since as you can see from the range 6000 to the end of the memory, we are not using any of those addresses. For example, we can use those addresses to, for example, let's say leak 0x4000, or let's say 400. Let's, for example, leak uh leak a leak 0x400. Yeah, since all the bytes that we have basically we have basically 0x 1000 in the RAM. We will try to leak 0x400, obviously bytes. Well, it's not like in the RAM, but in